Hey, we're going to work some problems like you might see on test 5 here. I'll try to do these quickly, but of course if you have any questions just let me know. This first one is about density, looking for mass, and we know the density and we know the radius and the height of these things. So of course we're thinking about the formula density equals mass divided by volume, and I kind of need a little picture here of this thing. If I had a cylinder, it would look like that. They're telling me that the radius is 4 centimeters and the height of this is 3 centimeters. So I've kind of got a choice here. I either need to go to centimeters, keep it in centimeters, or move it to meters. That's a choice I get. I look at the density here, 9.52 grams per cubic centimeter. With that number, I would probably just leave this all in, centimeters here, centimeters there. This is going to work out. It's going to give me a number in grams, and then I could move that to kilograms if I want. Let's leave it alone. If I'm looking for the mass, I need to multiply both sides by the volume rather. So I've got myself 9 point. Let's see. Actually, one more step in here. If I leave the density, the volume. I need a little bit of middle school geometry here. The volume of a cylinder is equal to the area of the bottom, or the top, forget it, which is going to be a circle, pi r squared, and then the height right there. Okay, so just putting the numbers in, 9.52 grams per cubic centimeter times pi times 4 centimeters squared times 3 centimeters. That should be the mass of this thing. If you know what you got, you can look up the density. But the only thing I probably should have done was put this right here instead of right there. The reason for that is I need to square the 4 and the centimeters. So let me correct that a little bit real quick. Here comes my numbers, 9.52 times pi, that's right here, so second caret, times 4 squared times 3, and that would be 1436 grams, 1,436 grams. If you want some kilograms, just convert it over, move the decimal place 1, 2, 3 times 1.436 kilograms. And I'll put a circle around that because we tend to prefer kilograms. Right here I got a water tower. It's way up high. The water is up here, and we're interested in a point down here. Now one way to phrase this problem is you got yourself a water tower like here, and there's a pipe that comes down or something, a little spigot right there, I guess, that the water's going to come pouring out of, and it's going to come out faster because it's got all this water stacked on top of it pressing down. The gauge pressure, really easy to find, G-A-U, it's not easy to spell apparently, but rho GH right there is all that I have to do. This rho is the density of water, would be 1,000 kilograms per cubic meter, and I'm making sure to use that one instead of 1 gram per cubic centimeter simply because of the units. I want the units to be happy here. I want you to be happy. I want the units to be happy. And see how this one's got meters and seconds and that one's meters, so I need meters here to make this work out. Now when I punch this thing up, I'm going to get the number of this thing, and it's going to look like this. I'm going to have 1,000 times 9.8 times 35. I'm going to get 343 somethings. So it behooves us to find out what the units of this would be. And that isn't hard to do because right here I've got a kilogram and a meter per second squared. That's going to make a Newton for me. And then this meter right here is going to cancel one of the meters, not all 3 of them, but one of them. So I'll have meters per second there. And of course that's a Pascal. All right. So the units worked out fine here, and I would just put that as 343,000 Pascal. Okay, now that was the gauge pressure. To do this second part, find the absolute pressure, what I need to do is to take the gauge pressure if I swam down there with a pressure gauge, or if I put a pressure gauge on the pipe right there, this is what it would read, meaning that the pressure at the outside air right here, at some other point would be 0 Pascal. All right, and the pressure here is 343,000 above that. But if I want the absolute pressure, then I've got to come in here and add, I got to add atmospheric pressure, which has a value of 101,300 Pascal. So when I add that much, I'm going to get 444,300 Pascal as the absolute pressure. Okay? And so there's kind of two answers there. There's two different values of pressure, and you need to make sure you know which one they want, like that. This is the pressure due to the weight of all this water stacked up on that point right there. This number, the absolute pressure, says, hey, wait a minute, I also have all of this atmosphere that's stacked up on top of the water, which is stacked up on top of this point here. So if we're including the pressure due to the atmosphere, then I've got to add the atmospheric pressure and get the absolute pressure. Interestingly enough, there is another way this problem can be phrased. Very simply here, if we had a swimming pool or a lake or something like an ocean, and we were going to swim down to a point, some point down here, if that were 35 meters down, about 110 feet or something like that, we would have the same pressure. Whether the water's stacked on top of you going up in the air, whether you're buried underneath that much of it, same math, same physics. Right here I've got a hydraulic press, and we know enough to draw the little picture for this thing. I need a small hole here, cylinder going down, and a big hole on this side. And there's going to be a piston on this side which can move up or down, and a bigger piston over here which seals this thing off. It can move up and down. And what we're going to do is push down on this side with some amount of force. Right here in the problem they tell me that's going to be 50 newtons. So that's F1 is 50 newtons. And then this thing is going to move up with some amount of force F2 right there. And if you put this thing under your car, it'll pick your car up. If you put it under your house, it would pick your house up if it's strong enough or whatever, right? So the other numbers that we need here would be the diameter of the small hole, the diameter of the big hole, and we've got those. D1 equals 2 centimeters, D2 equals 15 centimeters. Now, we could argue about the units on this thing, but it turns out they're going to cancel out. The formula that I use on this is that the pressure on side 1 has got to equal the pressure on side 2, because for this point and this point, this is a fluid. It can all move around, and it would. If I had high pressure on one side and low pressure over here, well, then it would flow. It would move and balance out. So the pressure at those 2 points has to be the same, and pressure is simply force over area. And area is, in this case, pi r squared. And when people mess this problem up, it's that little squared right there that gets them. They forget to square it. Now, you can see that the pi on the right and the pi on the left are going to cancel. So that goes away. We don't have to worry about that. You could also put diameter squared in this. That would work. Technically, there would be a divided by 4 under here, and that would also cancel. But this will work fine here. So if I'm going to use the radius, I'd need to cut both of these in half and put those numbers in. And I've got 3 of them. I've got F1 and R1 and R2, and I'd like to see what F2 is going to be, so you can see where that one's going. Now, this second part of it right here, they're asking about the distances that this is going to move. So if one side goes down 12 centimeters, I'm going to call that L1. Length 1 is 12 centimeters. This one's going to go up some amount right there. And there's 2 ways to get this. You can either say that the work done on side 1 has got to be equal to the work done on side 2, and of course work is force times distance, and this would be F2L2. Plan B here is to go about with the old volume of the fluid on side 1 is going to equal the volume of this fluid on side 2. When this piston goes down to, let's say, right here, then I've moved this much fluid right there. That much fluid comes over, it displaces, it comes over here on the other side. I'm going to take that much fluid on a bigger plate. I'm not going to get a whole lot of height out of that. And you can see the difficulty that I'm having here drawing this thing, but you know, I might get just a little bit whenever I push this one down a good ways. So I'm expecting a smaller number here. Volume, of course, is the area. The area of both of these is a circle times the height. So I could write A1L1 equals A2L2. It being a circle, the area is pi r1 squared. And over here I'd have pi r2 squared. So I can cancel the pi's. Lost the squared right there. Don't lose the squareds. Those are important. So I could do it either way. By the time I get done with this blue stuff here, I'm going to have force 1 and force 2. They gave me L1. They want L2. We could solve for that really simply. I've got R1 and R2. I've got L1. So I could solve this thing for L2 right there real simply as well. Either one of those will work. All right. Right here I have a 200 kilogram crate that's hanging straight down from a cable. And a rope is going to pull 500 newtons to the right. And we'd like to find two things: the tension in the cable and the angle that the cable makes with the vertical. So I'm going to label some stuff here. This is gravity pulling straight down, mg. This is, I'm going to call R for the rope that's pulling to the right. And this will be T. And there's that angle that they're looking for, theta, measured relative to the vertical. All right. So this is really a hanging mass problem. And you remember that with a hanging mass problem that you always want to do two things. You want to make sure the sum of the forces in the x direction equals 0. And the sum of the forces in the y direction have also got to equal 0. That box is static. It's not moving up or down. So I build an equation to say don't let it move up or down. And it's not moving left or right. So I need to make sure that the x component of t cancels out any rightward pull from r. That the left and the right cancel out. That the up and the down cancel out. All right. So I get busy over here looking for x components. So let's switch to blue for x. And t is going to pull this way. I'll call that t sub x. It's opposite. Right here's theta straight across. This would be the opposite. And so I got to use sine for that. T times the sine of theta. Meanwhile, r pulls to the right. So that's an x component. This guy doesn't pull left or right at all. So I only have those two to put in my expression. And I'd come along and say minus t sine theta equals, minus plus r equals 0. I got two arrows, t sine theta, r. This one is left, so I called it negative. R is to the right, so that's positive. And I've got a nice little expression there. I do know r. I don't know t or theta. Let's put in what we do know. And I'll have negative t sine theta plus 500 equals 0. Okay. Two unknowns, t and theta. I can't really solve anything there yet. So let's go build the other equation. In green, I'm going to have anything that's lifting up or down, y direction forces. Well, t is certainly pulling up. So t sub y is going to be t times the cosine of theta because it is adjacent to the angle. R does not have a y component, but this does. mg, it's all in the y direction. So in the upward direction, I'd have t sub y. And let me just write, go ahead and write t cosine theta right there. And then down, opposite direction, negative sign equals minus mg. That equals 0. And I've got some numbers there, t cosine theta minus 200 kilograms times 9.8 meters per second squared is g, and that's equal to 0. And 200 times 9.8 is going to be 1960. Is that enough? Yeah. Okay. So I've got this curiosity here, and somehow we got to solve this. There's a little trick here. One option would be to do substitution. I could solve this one, say, for t, and then plug it in over here. Solving for theta is a little trickier, so I probably wouldn't do that. But the easiest way of all to do this thing is to take the first equation and divide by the second equation. I take t sine theta. You know what I should have done? I should have moved that 500 over. And let me take one more step before we do this. I'm sorry. I get excited about these things. How about if we say negative t sine theta equals negative 500, and then I could get rid of the signs, those negative signs. T sine theta equals positive 500. Multiply both sides by negative 1 right there. And then we'll do the same thing with the green equation. We will write t cosine theta equals 1960. Just add that to both sides. All right, now let's stack these things up, see what happens. We'll take the first one here, t sine theta equals 500. I'm taking the left side of the first equation, dividing by the left side of the second equation, like that. And then I'll take the right-hand side of the first equation and divide by the right-hand side of the second equation. And it'll look like that. Now, the reason this is a nice way to do this, and I've already said there are other ways, the t's cancel when you stack that up. Furthermore, sine over cosine is always going to turn into tan theta. And so this is kind of like a little quick way to get yourself out of that mess. 500 divided by 1960 is going to be about 0.9, I'm sorry, 0.23 or something, 26, yeah. So 255. If I do the arctangent here on this thing, second tan of the last answer is going to be a 14-degree angle. Theta equals 14.3 degrees. I think I got my decimal right. Yeah. Okay. So that is this angle right here, and that's one of the things they wanted us to find. They also wanted the tension here in the line. So now that I know one of these things, I could take this and plug it back in either here or way over here and solve for t. Doesn't matter which one. Why don't we do the blue stuff? I got a little more room over there. So if I take that 500 that's on the right and divide by the sine of 14.3, then the tension in that cable is going to be 2,024 newtons. Okay, so there's the two answers they wanted. Number 5, I got a beam problem here. 20-meter beam, got to have a picture of these things, so let's get busy. There's my 20-meter beam, and I've got an upward force at each end. It's supported at the ends by two walls. So the left-hand wall is going to push up right here, and we could call that F1 or something. The right-hand wall is going to point up right there, push up. It's going to hold those two ends up. The walls push up. The beam weighs 1,800 newtons, so that's going to be straight down. And that acts right in the center. And then there is a air unit, an air conditioner, some kind of big heavy thing, 3,200 newtons, 3 meters from the right wall. Here's the right-hand wall. Come back 3 meters and put in your other force right there. 3,200 newtons is that one. Okay, how strong do the walls have to be here? Would be the big question. So we're looking for F1 and F2. like that. Now I need to put some of these numbers in there. Seeing that I have two unknowns, I'm going to pick one of those two unknowns as my pivot point, and it would be probably easiest just to pick it over here at the left-hand side. You remember that as soon as I pick a pivot point, I want to call that pivot point 0. So this is 0 meters from the pivot point to that arrow. I need to know the distance from the pivot point to each of these other arrows. And all the way over was 20 meters. The weight of the beam acts smack in the middle, so that would be 10 meters. And then I had 3 meters here, so if I take 20 minus 3, that would get me to 17 right there. So now I've got a pivot point picked. I've measured all my distances from the pivot point, and we're ready to build a torque equation. Sum of the torque equals 0. And I have 1, 2, 3, 4 forces, so I'm going to have 4 torques. F1 times 0, 1800 times 10, 3200 times 17, and some unknown force F2 acting at 20, and together all of that's going to be 0. F1 times 0 is 0. That one's gone. I need to figure out my signs. You know how to do this. We draw a little arc over here, and when I drive a nail right here through the pivot point and hold this end stationary, then this end is going to swing either up or down. That force is going to try to make it swing down. So we could call this one a negative torque. This big heavy air unit is going to try to make this one swing down, negative direction. And this guy is going the other way. It's trying to rotate it up, counterclockwise, opposite direction, opposite sign. Okay? I usually call rotating it counterclockwise positive and clockwise negative, because that's how we measure angles and trig and everything else that we did. But you can do this any way you want. Okay? So that's my deal right there. And I'd probably grab my calculator and get me a number for all of that. And in fact, I'm going to add that to both sides. So let's just make them both positive. I'm going to go ahead and add as I go here. And I'd have 1800 times 10 plus 3200 times 17. And I end up right there, 72,400. Remember, I added those two terms to both sides. That should be in Newton meters. This is a Newton, that's a meter. This is a Newton, that's a meter. And there's nothing left over here except F2 times 20. So if I divide that by 20, I'll have F2. And that would be 3,620. Meters are going to cancel there. Leave me in newtons, which is measurement of force, so that looks good. All right, and now we know that one. Okay, 3,620 goes right there. And you can't see it because it's on top of that other mess, but you get the idea. I don't have this one yet, so I'd like to come back and do that one. D2L is going to ask you for one or the other one. It can't ask you for both because it can't think about two things at once. But the easy way to get the other one is to say, well, I know the sum of the torques equals 0, and I've already successfully done that. The other rule is the sum of the forces better be equal to 0. So if I just come through and get just the forces here, I don't care about the distances. I don't need a pivot point. I don't have to do anything except put in the other forces and make sure that they add to 0. So that's not too hard. I'm going to add this to both sides, add that to both sides, subtract this from both sides, and I can just do that straight way here, adding 1800, adding 3200, and subtracting 3620. Then the left-hand wall needs to support 1,380 newtons. Okay, here's another beam problem. This one's got an angle in it, so we call this a boom problem. There's a boom sticking out from a wall. It says the whole stick is 3.2 meters. We'll go ahead and put that right here for the distance right there. Now I'm measuring from the wall, and that's a good pivot point on all of these boom problems because there's a whole bunch going on right there, and I don't want to think about it. If I pick this as my pivot point and call it 0, then I just knocked all of those forces out of my torque equation, and I'm good to go. They tell me that this thing has a mass of 12 kilograms, so the stick's mass is centered up right there, and I could take that mass of the beam times G and get the weight of that thing. I need a force, so convert it to weight. That was 12 kilograms times 9.8. Got myself 117.6 newtons right there, like that. Now there's also something else hanging on here. I got 500 kilograms. That is 0.6 from the right hand side. So that's some downward force right there. I got 500 kilograms times 9.8 meter per second squared, and I think that's going to be 4,900, but let's make sure. 4,000 times 9.8, 4,900 newtons, like that. And I need to know where it's acting. I need to know where both of these are acting, right? I've got to have all my distances. The whole stick was 3.2. Half of that would be 1.6 meters. So that's the where the weight of the stick acts. And they tell me that this thing is 0.6 meters from the right-hand end. So if this is at 3.2, I need to subtract 0.6, which will get me to 2.6 meters for that guy. All right, I've got all my distances measured from the pivot point. I can build a torque equation. And let's forget about the wall. There are forces there, but I picked this as 0, my pivot point, so I don't need to worry about them. I've got 117.6 acting at 1.6. I've got 4,900 acting at 2.6. Those are both trying to pull the stick down, but then this tension right here, this cable, is holding it up, canceling that out. So I need those three forces. Here we go. 117.6 at 1.6. I've got 4,900 at 2.6. And then I've got the tension at 3.2. But there's one more little wrinkle here. There's an angle on that thing. And anytime I have an angle on a force right there, then I've got to come back and fix this thing. I only want the y component opposite that thing, so I need to toss in a sine theta right here, and that theta was what, 22 degrees. So let's go ahead and put that in, 22 degrees, and that's all equal to 0. Only thing I got to do now is get my sines. I draw my little arc over here. Anything that makes it rotate up is positive. Anything that makes it rotate down is negative. And so you can see that this guy is going to be negative. This one's going to be negative. This one's going to be positive. And I turn the crank and get T right there. That's not too hard to do. I'm going to add both of these things to both sides. It's going to cancel on the left. Times 1.6 plus 4,900 times 2.6, and that's equal to that much. I need to divide by 3.2, and I also need to divide by the sine of 22, and there's the number. I'm going to hit mode and just make sure, yep, I'm in degrees, so that looks good. 10,784, let's round it up to 85 there, maybe even 10,800 or something. 3 significant digits probably ought to be enough. But that's the tension in that cable. And tension is a force, so this would be newtons right there. All right. It would also be possible now to come back and say, well, how hard does the wall push this way on the stick? How hard does the wall push up or down, and get the force that the wall puts on the thing? Of course, you just use the rules. Some of the forces better be equal to 0. That's true in the x and the y direction. Shouldn't have to use a torque equation again, but it's there if you need it. And so those are the only rules to statics. And once you can apply those to a picture, then it's pretty straightforward. Right here, number 7, we're going to move a rock. So let me draw the rock. Big honking rock. We're going to jam a stick up underneath the end of it right here. And here's another little rock. A little fulcrum is the pivot point thing that we have right there. And so basically we're going to push down on this side, and this end's going to go up and lift the rock. We're going to get a multiplication of force here because of the distances involved. I've got more torque. There's more moment arm on this side. So I need to know how much force I'm pushing down with. That's what I'm looking for. It says that from my hand to the fulcrum is 1.6 meters. Here's my pivot point. And all the way to force 1 is 1.6 meters, so that's my distance on that side. I've got 0.15, almost a tenth, a little bit less than less than a tenth would be the distance from the pivot point, the fulcrum, to the rock. 0.15 meters right there. Now they told us that the mass of this rock is 110 kilograms, so gravity is pulling down with mg, and that's the force that it puts on the stick. I'm really thinking about the stick here. What happens to the stick? And it's got 3 forces on it: me pushing down, the rock pushing down, and the fulcrum pushing up. Because I picked the pivot point at the fulcrum, I don't care about the fulcrum. So it's really down to these two. It's a little seesaw kind of problem. You could come in here and say the sum of the torque equals 0, and that would be F times 1.6, and I've got mg, 110 kilograms, times g, 9.8 meters per second squared, times its distance, 0.15, and that better be equal to 0, okay? And that would work just fine. Should have put a unit in here because I put it everywhere else. Can't get it in. Okay? Now, my thing is going to rotate the stick one way. The rock is trying to rotate it the other way. If we draw a little arc like we usually do here and call up positive, you can see that when I push down on this side, it's going to lift the other side up. If you hold your pencil at the fulcrum and push down on the left, the right hand end goes up. So I would call this one positive right here. And the rock is going to try to do the other way. It's going to try to push this end down, negative. Okay, so that'll work fine right there. And all you got to do is solve for this. Multiply, get a number over here, add it to both sides, divide by 1.6, boom, you got it. Right here's some fluid flow problems. So the speed of the water in a pipe is 0.54. It reduces to 5 centimeters. I got a big pipe. 25 centimeters, that's a real big pipe, and then it goes down to 5 centimeters. That's still a pretty good sized pipe. Okay, but I would write those down. R1 equals 25 centimeters. Maybe we need to make that meters. We'll find out here. The velocity on this side is 0.54 meters per second, and they're asking us what the velocity over here is. Now I got this thing called the equation of continuity that says when fluid flows, I can't have it stacking up somewhere. There's nowhere in that pipe to store fluid, so whatever fluid flows here, that same rate of flow has to flow over here, which means it's got to go faster to get the same amount of water through a smaller pipe. It's got to go faster. The formula that we need is A1V1 equals A2V2, and area of course is pi r squared. Pi's are going to cancel. Don't forget to square the radii again. You could use the diameters in this as well. Diameter 1 squared V1 equals diameter 2 squared V2. That would be fine. Either one. So if you want to cut the 5 and the 25 in half and put them in here, that's great. If you want to just use 5 and 25, you'll get the same answer down here. So I don't really care. We are looking for V2, and that would be D1 V1 divided by D2 squared equals V2. Run the numbers, see what you get right there. Tell you what, actually I need that number because the next problem is going to use it. So let me put this stuff in. Diameter 1 was 25 squared. The velocity was, I have no idea, 0.54. And then I'm dividing that by the small pipe, 5 squared. Okay. Now the reason it's okay to leave this in centimeters is that it works out fine. If I use the diameter here in centimeters, and that's squared, and the velocity is meter per second, that looks pretty bad, doesn't it? But the units on the bottom would be centimeters squared. And see how the centimeters squared on the top cancels the one on the bottom, and I get meters per second. It's okay. All right. If you feel more comfortable going to meters, go for it. But then you'll have meters squared, and they're still going to cancel, and so you'll get the same thing. All right, 13.5 meters per second. We actually need that one for this one as well. I've got a pipe. It starts out 25 centimeters, goes down to 5 centimeters, except this one's going way up high. There's the big pipe, and it's going to go up to the 6th, 8th floor, whatever this thing is. Dang it. And turn into a little bitty pipe that will make the water fountain go in the sink and the toilet and whatever else you have. All right. So diameter 1 is 25 centimeters. Diameter 2 is 5 centimeters. This one's on the ground, so I would call the height here 0, and then it goes up 22 meters. So I'd put those down. And we just found the velocity for this. Velocity 1 was 0.54 meters per second, and the number we just got, V2, was 13.5 meters per second. It's got to speed up a whole lot to do that. And then they give us one more number here. The pressure at the top. All right, P2 equals 530,000 Pascal. And they want to know the pressure at the bottom. This is a very real problem. Every time you build a building that's more than, I don't know, a couple stories tall, somebody's got to come along and say, do we need a pump to get the water up to the top floor? The water pressure that the city puts out provides a little bit of that, but it won't pump it to the top of the Empire State Building. You'd have to get yourself a pump and run it up there, and this is how you do that. Okay? Bernoulli's equation is what we need. And the only real difficulty here is having enough space to write all this mess out and to make sure your units work out nicely. Okay? So I'll remind you that Bernoulli's equation, P1 plus rho GH1 plus 1/2 rho V1 squared equals P2 plus rho GH2 plus 1/2 rho V2 squared. All right? Now, turns out that to do number 9, I didn't know V2. But because we had just done that problem with a pipe that went from 25 centimeters to 5 centimeters, we already had that one. If somebody just handed you this problem, you'd have to do number 8 and then come in here with number 9. But the good thing is you wouldn't need the diameters anymore because you used that in the number 8 part. So I can just kind of scratch through that, and you can see those are the 6 variables that are over here in my expression. We're looking for the pressure at the bottom, P1. So I need to subtract these two terms from both sides, and actually H1 being 0, rho times G times 0 is 0. That one goes away. If I could just move that 1 over, then we'd be okay. All right. And I've got this number, that's 1,000 kilograms per cubic meter. Let's say 530,000 Pascal. Plus, right there, the density, 1,000 kilograms per cubic meter. This is one where you probably want to go with standard units. See that meter there? It's got to match a meter down here, and the height was 22 meters. It's got to match. Okay. Last time we kind of slid on it and worked fine. This time not so much. So just watch your units. Make sure you're doing the right thing. I need V2 squared. That's 13.5 meters per second squared. And then I've got this last term here, minus 1/2 rho times 0.54 meters per second, again squared. Okay, so I'm going to start up here, and you'd have to do all that, and that's a big mess. But you've learned to talk to your calculator. It's not that big a deal. Let's clear it out though. 530,000. There's my pressure at the top. I need to make sure I've got enough pressure to push that up there to a height of 22 meters. So I need to multiply, or get that term in there. I need to make sure I've got enough pressure to get this thing moving at the top. So I add that. And then I get credit for the velocity at the bottom, the kinetic energy at the bottom, you could almost say. As long as you don't forget to square those, as long as you get your signs right, as long as you keep the units consistent. I need 841,000 something Pascal at the bottom, P1. Probably going to need a pump. Okay. But that's something that you could check out there. Just a couple more. These are buoyancy problems. These are fun. Right here I've got a metal cube suspended in water. Guess what? If you put metal into water, it's going to probably sink. So this one's got a string that pulls up on it. And I'm going to put T. I get a little bit of help from the buoyant force. And gravity is pulling down. And every buoyancy problem, everything submerged in water, floating in water, whatever, you need to draw that picture and say, I've got this many forces on it. And then you can come in here and say the sum of the forces equals 0 because it's just suspended there, hanging in the water. It's not accelerating up or down. And I'd have T plus F sub B minus mg equals 0. All right? And the buoyant force, of course, is the density of the fluid times G times the displaced volume. Well, shoot, man, the whole thing's displaced. It's all the way underwater. It's pushing a volume of fluid equal to its own volume out of the way. It's going to look like that. All right. So we are looking for the force. I called it T, and then I switched to F. So let me change that to a T. Okay. Big T. All right, that was Mr. T. I've got, this is in water, so this density right here is 1,000. That's okay. Well, it wouldn't hurt to put density of the fluid. I got G. I know the sides on this thing, so I can get the volume. That's fine. I know G. This guy, though, is going to give me a little bit of a trouble. Here, that mass. They didn't tell me the mass of this thing. However, they did tell me the density of it. And I can come over here on the side and say density equals mass divided by volume. So mass equals the density of the metal times the volume of the metal. And slip that into my expression. All right, and it is important to keep separate the density of the water and the density of the metal there, of course. But what are we looking for? T. I'm going to go ahead and add that to both sides, subtract this from both sides. The density of metal, G times the volume minus density of the fluid times G times the volume. And all these numbers are known. Here's 6,500 kilograms per cubic meter times 9.8 meters per second squared. The volume, 6 centimeters on a side. We certainly don't want 6 centimeters going into our thing here because everything else is in meters. So I'm going to change that to 0.06 meters, and then it should be happy. I'm cubing it because that's on a side. The volume of a cube is equal to the side squared. Cubed, rather. And would look like that. Over here, the density of the fluid is 1,000. This is in water. Kilogram cubic meter. Got 9.8 meter per second squared. I got 0.06 cubed. Okay? Go for it. You can do that. And that will be how much the string has to pull up. All right? Buoyant force helps a little bit, but I got to hold it with a string too. Here, I got a wooden block that's floating. I believe this to be the last one. So, lucky you. Here's a block of wood. It's floating in gasoline, and this part is underwater. That is my displaced volume right there. There are two forces I need to worry about. One would be gravity pulling straight down, and the other would be the buoyant force pushing up. Now, on the last one, I had a string. I had tension. No string in this problem. It's just floating. So those two forces cancel out, and I can come along and say the sum of the forces equals 0. So the buoyant force minus mg equals 0. I could have just jumped to F sub B equals mg. Since I know those have to cancel out, then I could write it like that. Here again, this is the density of the fluid times G times the displaced volume. Last time we counted the total volume because the total volume was displacing water. Here, only that part underwater counts like that. We're looking for the density of the block. We're going to have to pull that same trick again. The density of the block equals the mass of the block divided by the volume of the block. So if I multiply both sides, I get mass equals the density times the volume. So we're going to do that again. Density times volume. I already had a G in there. Slap that on. Would look like that. I got a G on the right and a G on the left. We can get rid of that much. There's one little simplification here that you can do. This displaced volume, it's 64% underwater. So 64% of the total volume is underwater. So I can come in here and go 0.64 V equals, over here I had the density of the block times V. And you see the V on the left is going to cancel the V on the right. All I got to do is take the density of the fluid, which is given to be 0.7 grams per cubic centimeter. I'm going to leave that one right there. Multiply by 64% or 0.64. That'll be the density of the block. Shoo! All right, so there's the last one of those. Just some little practice problems. Hope that helps. Call me, talk to me, text me, whatever, and we will figure out what we can do to help you out here. All right? Thank you. Have a good day.